Welcome to this lecture in the Faculty Development Program, which is organized by Ganga Institute of Technology and Sciences. And I must thank Dr. Vanna Arora for giving me this opportunity to interact with you. Uh, in fact, this is very interesting topic actually. So, Vanna Madam asked me like what can be the possible topic on which I can deliver. So I thought I need to deliver only one lecture, so I have mentioned three different topics. So she put one topic, metal additive manufacturing, which we discussed on Monday lecture. And the other two topics were hybrid manufacturing and smart manufacturing. So she just combined these two topics and said, sir, your second lecture will be on hybrid manufacturing and smart manufacturing. Now, I told her also later that I don't know really what to talk because both of them are very huge topics. But then her point was that it's already circulated, everything is done. So it's now my headache. So I'll try to do justification.
Sorry for that, sir. Extremely sorry for that.
No issues at all. That's the fun part of the teaching also. That's where you also learn many new things. It's always easy to speak for a longer duration, but once you have to press the points in a very short duration, that's what is more important. So actually, I was wondering even till 5 minutes before this lecture, what I should present, what I should not present, because I have huge data which can be presented both for hybrid manufacturing and smart manufacturing. Interestingly, the three topics which we picked are my current research interest domains also. So hybrid manufacturing is one where we are extensively working, and we have multiple sponsored projects also, huge projects also. Smart manufacturing, I have recently got one project, but that's an area where I am actually moving into because the future is all about Industry 4.0, IIoT, and smart manufacturing. Interestingly, in our institute, IIITDM Jabalpur, from this year we have started an undergraduate program in smart manufacturing also, BTech Smart Manufacturing 4-year program, which will be offered by Mechanical Engineering Department itself. So it was a tough challenge. So what I thought was, let me just give you a bird's eye view of both the processes, and not through the data which is available on internet or which is available on websites, textbooks, but through the work which we have carried out in our laboratory. So most of these slides, except for some preambles where I need to introduce the things to you, are the actual images which uh, my students have worked, my research staff in the group has worked on these topics. And in fact, at the end, I thought I must put an acknowledgement slide acknowledging all those people who have worked on those things. So the slide obviously spilled over to two different slides. And even I was not sure whether I am talking about everybody I have left. So I thought that rather than naming them, I'll begin my presentation by acknowledging all the doctoral and graduate students, those who have finished their PhD or masters, or those who are doing their PhDs or masters, who have contributed immensely to the development of the lab and the research agenda of the group. So my talk will begin with thanking those set of people who have really worked day and night out to give me an opportunity to share their results in front of you. So most of them are their results, which I'm taking liberty to share with you. So again, this is a pruned down list, but yes, this is what I intend to cover up in this 1.5 hour of lecturing. I'll try to finish it sometime before, so that I have some time for answering your questions, and I expect that you would be having multiple questions. If I'm going beyond 1 hour 15 minutes, please somebody give me a reminder that I have to wind up my presentation so that we can have some time for discussion. So we'll be talking about mixed hybrid processes, additive subtractive manufacturing processes, UVISF, that is ultrasonic vibration assisted incremental sheet forming, ISD, incremental stress drawing, deformation machining. Then we'll switch gears and talk about smart manufacturing, industrial internet of things, industry 4.0, cyber physical systems. We'll also try to compare smart factories versus digital factories, traditional factories, in terms of technological gaps. Then I'll tell you one interesting thing that is digital thread for additive manufacturing, and wind up with the additive manufacturing at our lab, the Logic Lab, in the era of smart manufacturing. That is how we have applied smart manufacturing to additive manufacturing in our laboratory. We did discuss about additive manufacturing in the last class and smart manufacturing. So combine the actual application of smart manufacturing for additive manufacturing that I'll be showing to you. So the first point which comes is, what is hybrid manufacturing? So it is basically a hybrid, as normally there are two different terms which we use. One is combined manufacturing and second is hybrid manufacturing. Combined are basically when you are joining two different operations. They may be sequentially one after the other, or maybe they can be recursively doing like 1, 2, 2, 1, 1, 2, these types of things possible. Hybrid is when two or more than two processes are executed simultaneously. That is only possible when you have simultaneous and control interaction of either process mechanism or energy sources or tools or a combination of these. So you have you take two different uh, process mechanisms, you join them and you make a particular process. That's a hybrid. Or maybe you take two different energy sources, maybe heat and mechanical energy, you join them. That's a hybrid manufacturing process. You use two different types of tools. uh, I'll take one example also, like additive and subtractive. That's also hybrid manufacturing. Or it can be a combination of these also. It can be, like, for example, uh, two different process mechanism with two different tools and two different process mechanism with two different energy sources. And the overall objective is to improve the process performance. And this is not my definition. There's a CIRP collaborative working group on hybrid processes which give this. And CIRP is a body of manufacturing engineers based in Switzerland, which is sort of de facto considered to be standard of manufacturing processes. This is somehow you can say you have multiple processes, 1, 2, 3, 4, 5, 6, n processes, and all these processes happen simultaneously. That leads to a hybrid process. Or in simple way, I can say hybrid process can be, as I told you, if you look at the left hand side, it can be a combination of different tools or different energy sources, which can be further divided into mixed processes or assistive processes. Or if you look at the right hand side, it is like, I think you can see my mouse. My mouse is visible to you, or maybe I can use a laser pointer. I think that will be better. So you can see this. So this is a controlled application of process mechanisms, which is also leading to a hybrid processes. So basically, if you look at this image, we can say the hybrid process can be broadly categorized into three categories: mixed processes, assistive processes, and the processes where you have controlled application of process mechanism. So look at based upon energy or tool are these two, and based upon process mechanism the third one. So let's try to look at the examples of these three types of hybrid processes. So mixed hybrid process, we can have EDM and ECM combined. What do you call these process? Anybody can tell me?
Subtractives.
No, what I wanted, one particular application such processes, like for example EDCM, electro-discharge chemical machining. Okay, but that is already established process.
Electrochemical discharge machining.
Yeah, that's what I'm saying. So, but I'm not talking about that. I'll not talk about that process. I'll just take EDM process, because EDCM is two different process mechanism. What we are talking about a mixed process where either the energy is same or tool is same, not process. So we'll talk about either we are using two different types of tools or two different types of energies, not two different process mechanism. So I'll focus on EDM and show you how a conventional EDM can be converted into a hybrid EDM process. Then assisted processes, they can be multiple, like it can be ultrasonic vibration assisted incremental forming, laser assisted turning, vibration assisted grinding, vibration assisted EDM, media assisted cutting, laser assisted bending. So for example, in all these cases, the turning is assisted by laser. Grinding and EDM are assisted by vibration. Cutting is assisted by some slurry media, and bending is also assisted by laser. These are all assisted processes. But what I'll be again, these are available in the textbooks also. What is not available, I'll tell you about that. That is ultrasonic vibration assisted incremental forming process. Then we have control application hybrid processes where you are talking about two different process mechanism and you're joining them. Like the first example which I'll be covering, and interestingly all these red I have marked red because I'll be covering as a part of my presentation today. We talk about incremental stress drawing, that is ISD, and deformation machining, basically which combines machining, which is subtractive manufacturing, and incremental shape forming, which is basically a forming or near net shape manufacturing processes. So previous case, this includes two different processes, stretching and drawing. This includes machining and forming actually. So this is where you are joining two different processes and trying to make a hybrid forming. So let's start with the mixed hybrid processing, EDM process. Again, I'll not go into the detail and process, but I'll try to cover up. So this is like some of the machineries which our labs have in the campus. If you look at from the top to bottom, this is basically abrasive water jet machining from Omax. This is EDM Electronica's EDM machine. This is a rapid prototyping machine of additive manufacturing machine of Stratasys. This is Ukuma milling center, and this is like a CNC turning center of IMCO actually. So these are some of the machines which our laboratory has, and we adapt these machines to carry out the experimentations in the domain of hybrid manufacturing. Then these are like sheet forming and sheet. This is a process of sheet punching, and this is a machine for sheet bending operations. So this is again for the sheet metal applications, Amada's machine which we have. So coming to EDM process. So EDM, what we are talking about, we as a hybrid manufacturing process where we use two different tools or two different energy sources is we talk about electrodischarge machining of insulating ceramics. Now, what's interesting about this is the basic definition of EDM process says that it can only happen for materials which are electrically conductive. And that's why the word discharge comes into picture. So it has to be electrical discharge, which is only possible if the two materials, the tool and workpiece, that is cathode and anode, are conductive. But once we are trying to work for insulating ceramics, we are talking insulators. So it's not conductive. So how do we go for electrical discharge machining of this? That's what I just wanted to show to you. So our objective is to machine insulating ceramic materials, and we have to also study the machinability of the conducting materials from the perspective of non-linearity of EDM. And we also worked on single discharge FE models to work on these things. The two images at the bottom shows the basically SEM images of the component, the insulating ceramics which are machined by our process, and the right side image shows basically the time versus distance versus time for generating cavity in an insulating ceramic. So this was the experimental setup. You can see this, you can evolve also the Electronica JNC, that is EDM machine. So we customized our machine with some systems that through which we can make even the insulating material conductive. So we put some work table, some tool fixture, all the things are the part of the tool itself, like dielectric reservoir, tool holder, control unit, servo system, tool electrode. These are water tank, work tank. These are all basically part of the machine. But we have customized, we have adapted this machine for our application. And these are like the tool electrodes and the workpiece which we have used. So you can look, this is like a copper tool, approximately 2.5 inches long. Then this is copper tungsten electrodes of different diameters, approximately 4 inches long. This is the turning. You can see the same copper electrode. The turning of the tool electrode to get the desired shape and configuration. And this is the alumina ceramic, the workpiece. Alumina ceramic is basically a insulating ceramic which we want to machine through EDM process. And this is like the conventional left hand side is the top left hand side is the CAD model, and the bottom is the actual uh, conventional fixtures which we are used for our application. And right hand side is the a modified fixture which is like magnetic field assisted EDM fixture for carrying out the for holding the workpiece for EDM applications. And this is like the development of setup for coating. So the entire setup was developed like we had a copper tubes, we have a band heater, we have a Arduino board, a LM35 sensor, some air pump, and these were basically set up for coating the material because it is an assisted process. So we have to look into the way we can generate the spark. So this is this is a screen printing setup. You can see that uh, we put an adhesive tape on the ceramic, and this is with the help of coating blade, and then we have a we create a cavity which is for screen printing mesh fabric, and this is like it looks like this. So this is to help initiate the sparking process. Then we also try to put the carbon paste electrodes uh, which were made using graphite powder and mineral oil on, so that they can be coated on the ceramics to generate the first spark. Now if anybody is having any confusion, let me make it very clear that obviously the if you have a pure ceramic material, you cannot generate the spark into it, and spark, for EDM process is necessary, because without spark the machining will not start. So what we do is that by some mechanism we try to generate first spark, then post first spark, the when the ceramic is burned, it leads to formation of carbon. So carbon soutes are deposited on the material that leads to further sparks, and the process continues till it's get terminated. So that's what our objective. So we for example in this case we are trying to put carbon paste, and this is like a bird's eye view of different techniques which we have used. Some were very successful, some were just okay and successful, some didn't behave as per our expectations, but yes, I'm just showing you all those which we tried to do. So this is like putting a silver foil coating on alumina to generate the first spark, a copper adhesive tape coating on the alumina, screen printing carbon ink coating, aluminum coating, carbon paste electrode coating, and copper metal plate, which is mechanically fastened to. You can see the mechanical. The white one is ceramic, and the copper plate was mechanically fastened uh, to the alumina to generate the initial set of sparks, copper being metal, and this led to ultimately transfer of sparks to the alumina, and alumina was also burned, or maybe it created. The second is example is what we try to do is abrasive water jet machining, and the uh, we modified the water jet machining to a slurry introduction of a slurry. So rather than a three-phase mechanism, we worked on a four-phase mechanism where we have abrasive, water, and slurry. Slurry we use gelatin. Gelatin is one type of polymer, or it's basically is obtained from the bones of any animals, and it was like it is like it's a very conveniently available in many places, some chemical factories actually. So this was used to bind uh, the the abrasive and water jet, so that the divergence angle of the abrasive jet is restrained and the energy beam becomes more focused. The objective of this entire exercise was to make channels, micro channels, because if without micro channels, if without slurry, if you use just abrasive water jet, then there's a lot of the curve angle is very large. It becomes very tapered actually. So you can see this image. This is relatively very controlled. This is the vertical image. This is the depth of the channel which is being created, and this is the width of the channel being there. And this, like you can see, the conventional machine where we had added one T slot, and the tank, so the tank was kept at a height. So at a height, and through gravity, this is gelatin tank. You can see also through gravity, the gelatin was fed into the abrasive water jet machining. Okay, and this was heating at the upper critical element. So these are like some rough surfaces at the bottom, smooth surfaces at the top, improved surface finish. This was the channels which we tried to form actual operation, and this was like intermediate image of the 3D profiling which we have done with the help of abrasive water slurry jet. Now, normally abrasive machining is considered to be a process for generating 2D profiles, but through this case we were able to generate 3D profiles also. Then we talked about we are going to talk about two different process mechanisms: additive subtractive manufacturing processes. So we are going for additive manufacturing and parallelly finishing them also. So this is like and this entire setup was developed on a CNC machine, CNC turning machine. So you can see we customize the process, and this becomes a funnel and a hooper through, and the band heater through which the molten material, there's a nozzle, molten material flows, and that leads to the deposition of the fabricated part. You can see some of the fabricated parts, and this is being a CNC machine on the same setup. Because this is leading to some rough surfaces, the entire process is being manufactured on machined, so that we can get the desired form or desired shape of the object being manufactured. You can see, like for example, some 3D shapes are being generated, and these are some tensile test specimens which are being generated. You can see the size also compared to 1 rupee coin, compared to scale, which is possible from here. Now this is a very recent process, ultrasonic vibration assisted incremental sheet forming, and to the best of my knowledge, only 3 or 4 research groups are working all across the world on this particular process mechanism. So this basically tries to enhance the surface energy and the volume energy of the object, and to get it at. So basically what we are trying to do is that we have a incremental sheet forming process. The incremental sheet forming process is very much similar to additive manufacturing process, but big difference. Additive manufacturing is for depositing the material, and it's a making the material in an additive manufacturing process. Incremental sheet forming also moves step by step, layer by layer, but then it is meant more for forming the component. So what we do is basically is that we start in this case also we start from the CAD model of the geometry, and just like you try to find out the tool path for manufacturing process, subtractive manufacturing process, we try to find out a tool path, although there's a big small difference. So in our case we use our own CAM software, not a conventional CAM software, and that gives a tool path for the geometry or incremental sheet forming. So it moves layer by layer, and the process keep on deforming the sheet. At the end, you remove the metal, and leaving the spring back effect and some process deficiencies, the sheet is being deformed incrementally, that is gradually, step by step, to desired geometry. So now what we have done is that rather than simple deformation with the help of a tool or a punch, that tool or punch is also moving in a ultrasonic vibration manner. So it is vibrating and deforming the component. So, and in the process, the surface energy is improved because you are imparting the tool, as well as the volume energy is also being improved in this particular case. So this leads to what we call is ultrasonic vibration assisted incremental sheet forming process. So this is a mechanism. You can see the entire process starts with a sheet which is horizontal, and it's being deformed gradually by in a step by step. We start with this particular process, and we keep on deforming into this particular shape. But rather than simply, this tool is also, the forming tool is also vibrating the ultrasonic frequency, just like this. And this leads to improved characteristics of the process. So this is the ultrasonic. Left hand side is the ultrasonic vibration transmission system, and this is the frequency measurement equipment, so that we can control the frequency as well as amplitude. So we had tried to work on different frequency, 20 kilohertz, 22 kilohertz, 24 kilohertz, with different amplitudes to look at the effect of ultrasonic vibration on the incremental field forming. These are some of the components of ultrasonic transducer, and right hand side image shows the simulation of the transducer, which is uh, basically uh, simulation of the entire process before we go for the actual forming option. This is a machine on which we have carried out the process. This is our older machine. Now we have one more machine also. So and these both the machines have been designed, developed, and fabricated in house. So this machine is a 8-axis machine. The other machine is a 10-axis machine, and we can install ultrasonic transducer on this particular machine, which moves ups and down and deform it. This is a vertical machine, like where the tool heads are, the tool is moving this is Z direction, and the sheet is put horizontal. The other is a horizontal machine where the tools are moving from left and right, and the entire process is being done. So this is like, again, another bird's eye view, another look at the machine for the and this you can see the geometry of one of the very critical components, D shell, which is formed with the help of ultrasonic vibration assisted incremental sheet forming. So this is like the focus view of transducer belt and the forming tool, and these are the two cavities being generated. The left hand side is without ultrasonic vibration, and right hand side is with ultrasonic vibration. And I have not put the data over here, but you can see the depth which is obtained with ultrasonic vibration is much larger as compared to without ultrasonic vibration, and the quality of forming is also superior as compared to the previous case. So the advantage of UV ISF process is that it leads to better material flow, it leads to better surface quality, it leads to enhanced formability, and forming at higher feed rates is also possible, which are good advantages of introducing ultrasonic vibration with the ISF process. Next process is incremental stress drawing. That is, it is combining two different processes, stretching and drawing. So this is basically your incremental stress drawing process. So you are combining drawing and incremental sheet forming to lead to incremental stress drawing. Now this entire process is carried out in 3 stages. So the stage 1, the first stage is you do the drawing or the deformation process with a larger tool. Then you do the incremental forming with a middle size tool. That means this deformed geometry is going for incremental sheet forming. And finally, the third stage is you pick up a still smaller tool to go for this type of operation. So you can see we start with drawing with the large size tool, then a combined drawing and incremental sheet forming with medium size tool, employing inside out tool path. So tool will start from center and go outwards. And then finally simply ISF, so drawing plus ISF, and simply ISF with a small size tool outside in. So this application which we have carried out, for which I'll be showing the snapshots also. So this diameter of this tool was 30 mm, diameter of this tool was 13 mm, and diameter of this tool was 6 mm. So these are like different fixtures and tools which we have adopted. The left hand side shows the blank, the sheet which we have used, and we have put some cavity to provide it. You can see this is fixture with a ball, rolling ball support, and these are different types of tools which you say. So we have largest size tool 60 mm, middle size tool 30 mm, and small tool is 13 mm. This is the second set of operation which we have done. So we use two different types, two sets to go for drawing plus incremental forming and incremental forming. Then this was the drawing operation, and you can see it leads to like sudden jumping of the sheet from here, which led to even slight crack initiation also. But once it was uh, drawing was replaced by drawing plus ISD and then ISD rated, you can see the cavity being formed. And this also become, and these are like, this is a waste material which you have to cut later, because our object is only this much, the center portion where my laser pointer is moving actually. Then we talked about different types of setups. So this is a setup which was created with the help of ballpoint metal caster wheels, because the difference between, the fundamental difference between drawing operation and stretching operation is that in the drawing operation, you remember the basic forming operation, like you try to form cups and bowls with the help of drawing operation, the sheet has to flow. While in the stretching operation, which we do with the help of ISF operation, the sheet is supposed to be restrained, and we only try to uh, stretch that means the area of the sheet becomes larger and the process thickness decreases, because volume constancy law is there, volume will remain constant. So we have to design a setup which will facilitate both clamping as well as release of the sheet. So we tried different mechanisms. This is an example of ballpoint metal caster wheel. This is rollers in the base plate. So fixture we put rollers, and this is ball point, and through on the top of which the sheets were fixed. You can see we also used a different ball rollers which were meant to reduce friction at the base plate, and the right hand side is basically the component which is being formed. Ultimately this component has to be cut from here to get the desired geometry. Then we use different types of tools also. So one is this, hello, would you please keep your mics on, because some background noise is coming.
Abhay Sharma sir. Abhay Sharma sir, you are requested to mute your mic, sir, please. Abhay Sharma sir. Abhay Sharma sir, if you can hear me, kindly mute your mic, sir. Abhay Sharma sir. Abhay Sharma sir. Sir, it's okay now. Sorry for the disturbance, sir. And sir.
Sir, we are unable to hear you.
Sir has muted his mic.
Sir, we are unable to hear you, sir.
Sir has muted his mic.
Ma'am, if you can unmute him.
I'm requesting sir to join, sir. Wait. He's already in, but his mic is mute.
Oh, I'm sorry, my mic got muted actually.
Yes, sir. Yes, sir.
I don't know how. Am I audible now?
Yes, sir. You are audible now.
Okay, thank you. So this was okay. So these were different. So I was talking about this ballpoint tool where we copied the mechanism of a ballpoint pen riffle. So this is a ball which we have put in a tool body, and ball being free to roll, it was meant to reduce the friction. And then we also worked on the base plate with radial slots, and this is an example of a base plate with different radial slots to generate it. And now I'll show like the three stages. So this is a drawing operation which was done with the help of large tool. Then we used a medium sized tool of 30 mm diameter, and the tool path from out inside to out, and it was meant for both basically drawing as well as incremental sheet forming. and then we use a smaller tool of 13 mm diameter where it was pure incremental sheet forming, and this led to formation of this geometry. Later on we cut this with the on this side, and our desired geometry was obtained, which was much better than the conventional processes. And we have a comparative analysis also, so we could generate non-symmetrical shapes also with this. So when we were using crack ISF conventional ISF process, you can see it, the crack formed at a very small depth. But when we used a ISD process, so components were formed without crack, and up to a very large extent of depth was being formed. The dots you can see are basically meant for digital image analysis, digital image correlation (DIC) technique, and this at the zones of stretching, you can see there was a circle before this. After forming, the circles were converted into ellipse. So this helps us in finding out the major strain and the minor strain, which has come into the component. So what are the advantages of ISD process? Better material flow. We can control the wrinkling also of the sheet. The thinning got reduced in this case because of enhanced forming zone, and it leads to better formability as compared to conventional ISF process. Then we have deformation machining, where we try to combine machining with incremental sheet forming. So this is basically an operation which is meant for creating monolithic structures, single piece materials, and is being extensively used in aerospace, in automobile, in missiles, because assembly is considered to be bad for any components. So the idea is that whenever you're making a part, it should have minimal number of components. So that's what we try to capture in this particular process. So we have a thin structure machining, and we have a incremental sheet forming, and when we combine these two, this leads to deformation machining. So this is the schematics of thing. There are two different types of deformation machining. The first is deformation bending, and second deformation stretching. So in this case, we start with a block, and we do the machining operation with the end mill cutter and make this thin wall. So this part, this entire part is being removed. So this side is removed, this side is removed, and we get a thick, thin wall of height h and thickness t. And then we use a conventional ISF process, incremental sheet forming process. You can see this is a tool motion like this, and it tries to bend a straight wall into like this. So this type of geometry is not possible to be achieved by any other process. So this we call deformation machining bending. Second process is that we make a cavity, and this cavity is extended by incremental sheet forming like this. Okay, so we have a block, and rather than a cavity, a straight wall cavity, we have a conical cavity. This is known as deformation mode, stretching mode. And this is the actual operation what we did for bending on the CNC machining setup. You can see post machining, this is the forming tool, which is forming operation which has been taking place. And this is like tool path for deformation machining of the part. It's being done. The advantages, as I told you, like we can make monolithic complex shapes. That means with a single component we can generate complex shapes. No assembly is required. It provides better control over the properties of the form component. We are able to reduce the unnecessary weight, and that will lead to unnecessary cost of the components in comparison to conventional processes. It is also leading you to control thinning in the walls, and it provides better formability than the conventional ISF process. Okay, so this was I tried to go through very fast to cover some of the processes. There are many other processes which we are doing in our laboratory on the hybrid manufacturing processes. Like one interesting application, what we are doing is what we call as ETISF process, elevated temperature incremental sheet forming process. We are also working on micro EDM process, and we are also trying to combine additive manufacturing with ISF process. So these are some of the like interesting applications what we are doing. But knowing that the time is not time, we have already consumed half of the time. So let me change gears and now talk about the smart manufacturing. Now, smart manufacturing, this is the buzzword. So I thought let me give you a formal definition of a smart manufacturing. So basically, it's a process which is fully integrated, which works in a collaborative environment, and which responds to real-time challenges to meet the change in demand and conditions in the supply network, in the customer needs, via data-driven understanding, reasoning, planning, execution, all aspects of manufacturing process, and which is also uh, parallelly coupled with advanced sensing, modeling, simulation, and analytics technologies. And this is not my definition. You can see this is a definition given by Lu, Zhu, and Wang, a very recent paper, 2020. So this is the evolution of smart manufacturing. So I thought it's better to talk about smart manufacturing from the industrial revolution point of view. Uh, I think everybody is able to recall industrial revolution, first industrial revolution, which took place in England and Europe, and which started using the steam power to rather than mechanized energy, human energy. So steam power replaced the mechanized energy which was used to operate the machine. So most of the work before that was done with the human power, human hand, or even animal power, animal hands. But that was replaced by some machines which were powered by steam. Then almost a century later, in 1870, second industrial revolution took place in the United States, where the major focus was on electrical energy. So steam energy, first in the electrical energy second. In between, we have different application which led to the generation of the third industrial revolution also, like RFID was there, artificial intelligence was also there, mass-produced embedded systems was there, expert system, PLC, and then we talked about the third industrial revolution, which was basically took place in Japan, and it was like more like automation type of thing. Then we have like World Wide Web. We come into picture. Edge computing, cloud computing, Internet of Things, semantic web, big data, cyber physical systems, elastic compute cloud, and this led to the fourth uh, industrial revolution, which we are talking about now. And basically, um, it tries to replace the automation with the autonomy, basically. So uh, automation is when the entire machine is controlled by some sensors, some hardware. But autonomy is basically you have the flexibility to control the machine, and not only one machine but multiple machines. So it is similar to, like, for example, and it works in a collaborative environment. So maybe you want to work on some advanced machine which is located in Tokyo. So you will the design is done in India, in Jabalpur, for example, and some analysis is being done at manufacturing planning is being done at New York, and the data is passed to a machine which is located at Tokyo. And sitting in India, sitting at Jabalpur, you can control the operations of your machine which is located at Tokyo, either through World Wide Web, either through internet or through your mobile phones. So that is what you call is fourth industrial revolution, where you are replacing automation by autonomy. And I'll give you some other definitions also. And then this is another very interesting thing is that if so this is the fourth industrial revolution, where from Europe it traveled to United States, from United States to Japan, and from Japan to multiple locations all across the world. India is also considered one of the major destinations of industrial revolution. And then we have talking about after this was like uh, This was in 2011. Then we are talking about deep learning, fog computing, digital twin, which I'll be also talking about in aerospace vehicles by NASA, knowledge graph, AlphaGo. Okay, so these are different like evolution of smart manufacturing, again by a recent paper, the same paper which I mentioned earlier also. So coming to the background, what is the Internet of Things? Internet of Things is the interconnection among various hardware, embedded systems, and computer devices. The primary purpose is to send and receive data through internet or through WAN and LAN, and it encompasses the paradigm of smart cyber physical systems. So basically, Internet of Things is like there are multiple things which are interconnected by various hardware and various softwares through internet. So data can be transferred through internet with the help of WAN or LAN. Then we have also talk about so this is Internet of Things. So various hardware embedded computer systems. So this is like the way it looks like. So you can see your mobile phone, your car, your aircraft, some audio system, some printer, trains, hospitals, ship, even lighting. They're all connected through internet. And all these things are connected through internet. So we call them Internet of Things. Then we have one more I added to Internet of Things, that is industrial Internet of Things. So Internet of Things is when you join conventional devices and when you join the manufacturing devices, the industries, it becomes industrial Internet of Things. So and this leads to the concept of smart industry also. So you can see there's a user interface and this is an industry which is connected, which has some automation, which is controlled by big data, which offers flexibility. And this is like Industry 4.0. This entire paradigm is industrial Internet of Things. So what is the vision of smart manufacturing? So smart manufacturing is, if we start from the bottom to top, so you have factories, some physical things you can see. This is factory A, this is factory B, the factory C, which are connected together. So there is a standard connectivity and there is a cyberspace gateway. So cyberspace you are connected. So in the cyberspace you have some decision making optimization, some data collection and exchange. You also have modeling, simulation analysis, and data integration and processing. So you have cyberspace and we have manufacturing intelligence. And then we lead to some applications, which is smart production, production network, which is intra-business, inter-business, and business relationship between business and consumer, which is mass personalization. So we are even personalizing the device at a mass scale. So for example, you want to have one product as per your requirement. Your friends want to have another same product as per his requirement. So they can be, and you want multiple copies. You want to have manufacture in mass scale. That is possible by this particular technique, because everything is controlled by now models actually. So we know that, for example, when we try to buy, for example, our headphones or earplugs, musical earplugs from the market, they have standard sizes. Now human ears are not standard in sizes, so they have different dimensions. So there are some adaptability issues somewhere. Some people find it problematic to put the earplugs or the headphones in on their ear, so audio devices. But if we can take measurement of ears and everybody can have earplugs as per their ear sizes at the same price what they are mass manufactured, so that's a mass personalization. Okay, so we are talking about finally a smart production, a production network, and basically a mass personalization. This is what you call as smart manufacturing. So what are the design principles of smart manufacturing industry 4.0? So there are multiple dimensions, and this is again given by Ibrahimi et al. By a paper in 2019. So broadly, we are talking about interoperability. I'll come to all these things later. The real-time capability, the virtualization, the human aspects, the decentralized, and the modularity. So the design principles of smart manufacturing was industry 4.0 is that the system must be interoperable. So there must be connection between cyber physical system, people, and manufacturing system. There must be Internet of Things, Internet of People, and Internet of IoE stand for Internet of Everything. There are standards, protocols, and connected data. there's a collaboration, there's a cyber security, there's UPC, there's RTLS. Then we talk about real-time capability. We talk about real-time monitoring, real-time data analytics, real-time dynamic decision making, knowledge process interfacing, immediate data collection analysis, and real-time collection of sensor data. In the virtual domain, digital twins is the most interesting thing, and as I told you, I'll talk about it in detail later also. We talk about virtual models, diagnosis, descriptive and predictive analysis, knowledge process interface, sensor data, data analysis, and to readjust the model, ergonomics. Then just give me 1 second. Just let me have a glass of water actually. Shit. Okay, so okay, so this is like what I was talking about, and so you can see this. So we were talking about like virtualization, digital twins, virtual model, diagnosis, descriptive and predictive analysis, KPI, sensor data, data analysis, and then we also should be considering the human aspects, that is ergonomic, safety, social and psychological aspects, the decentralization, CPS is real-time decision maker, prescription, autonomous and semi-autonomous decisions, KPI, data analytics, decision-making rules. These are all decentralization process, and then modularity. Like the entire system should be in a modular manner, which should have flexibility, agility, dynamic configuration, customer orientation, and like many other aspects. Then the CPS has multiple layers. So there's a perception layer where we have hardware devices like sensors, aggregators, actuators, RFID tags, GPS. We have a transmission layer, cloud, internet, access point, Wi-Fi, routers, switches. Then we have some application layer, like for example, smart waste management, smart cars, smart transportation, smart traffic control, smart infrastructure, smart street lighting, smart water power management systems. Then if you look at the we have been using different terms, IoT, CPS, Industry 4.0 from this Venn diagram perspective. So you can see over here that industrial Internet of Things is a subspace of Internet of Things. Cyber physical system, as the name says, it is like system which is physical system which are connected to cyber, and the integration of IoT with CPS is basically Industry 4.0. So this is like how does Industry 4.0 look like? And when you compare smart factories with traditional factories, we have smart factories will have diverse resources, dynamic routing, comprehensive connection, deep convergence, self-organized, big data, limited fixed resources, fixed routing. That this is the like traditional factory. How does it look like? Uh, Fixed routing, shop floor control network, separated layers, independent control, isolated information, and so when you try to find out the technological gaps between the current manufacturing system and Industry 4.0, so this is the state of things, starting from the, if you look at the manufacturing concept, so these are like the digitization, communication, standardization, flexibility, customization, real-time responsibility, predictive maintenance, decision making, self-optimization, self-configuration. Then this is single station automated cells. This is current manufacturing system. And so we have some gaps between the current manufacturing system and the industrial systems, where, for example, we do talk about many things, like, for example, single station automated cells, automated assembly system, FMS system, SIM system, configurement systems. But then when you try to adapt it to Industry 4.0, then there are some of the issues which need to be resolved, and that can be done with Industrial Internet of Things. So if you compare IoT and IoT, so IoT is the network of physical devices, vehicles, home appliances, and other items embedded with electronics, software, sensors, actuators, and connectivity, which enable these things to connect, collect, and exchange data. The Industrial Internet of Things is a network of devices connected via communication technologies to form systems that collect, monitor, exchange data with different products, which are like these are like more likely, like, what do you say, is the industrial devices. So this is basically, as you can see, the bottom line over here. It is like for basically industrial companies to make smarter business decision making faster. So this is like uh, Industrial Internet of Things. We have smart factory, smart grid, smart machines, smart city, car, and consumer Internet of Things, which is like, again, these are all consumer appliances. These are all industrial appliances. So that's differentiate between both are have connectivity, proper connectivity, and all the both the cases the devices are properly connectivity. So we talk about connectivity, data analysis, and all those things. So if you look at the market of connectivity global between, basically, so we say that if you look at the IoT market, so the IoT market is expected to grow from 157 billion US dollars in 2023 to 457 billion dollars, with a compound annual growth rate of 25.5%. And by the year end, it is expected to be 300 billion dollars. On the other hand, if you look at the IoT market in India, it is poised to be 15 billion US dollars by this year, approximately 5% of the work market, and with nearly 120 firms which will offer solutions in the IoT segment. There will be tremendous opportunity for further growth. So if you look at this, so this is a typical Indian IoT market, which will start from more than USD $60 million investment. Their manufacturing unities, there are approximately 120 firms. The IoT startup has a share of 60 to 65%, and the investment which is made by Government of India in smart cities is close to US billion $1, and 55% is the share of industrial IoT revenue. And if you look at the different sectors, so there are various sectors which are working, starting from wholesale, process manufacturing, utilities, retail, discrete manufacturing. But like these are the red ones are the high impact sectors: healthcare, logistics, and utility. Although discrete manufacturing has the largest investment, but these are like the healthcare and logistic has the highest compound average growth rate, close to 25%, you can see. And this is the hype cycle, which shows like how does a thing rises and fall down. So you can see different, this is innovation triggers, what started, inflation of peak of inflated expectation, pro of delusionment, slope of enlightenment, plateau of productivity, and so on, which is being done over here. So Industry 4.0 is like this thing. I have already told you, like starting from mechanized machines to electrical to automation to autonomy by internet, connecting by internet. So these are like this is a smart factory, and this is how does everything is connected. So we have a suppliers, logistics,
Sir,
computer
sorry to
servers.
interrupt you, sir,
Sorry.
but can you please put on the slides show, sir? We are not able to see the slides moving, sir.
Sorry.
Kindly make full screen mode of your PPT, sir,
This is
please.
the full. I'm showing by full screen.
Oh, but we are not able to see, sir. This was happening yesterday also.
Okay, let me redo it. Actually, it is full screen. I have
Mm-hmm.
now taken out the full screen mode, and I am doing it again full screen. Can you see now? Full screen?
Not yet, sir.
To me, it's
Now it's okay, sir. Now it's okay.
Yes,
okay.
yes.
So, yes, sir. Now we are able to see.
Now it is all right, sir. Okay.
Now it's
Okay. So we are talking about sensor, digital production, physical production. We are talking about customized products, virtual production, smart products. So when we talk of uh, if you look at the different functions, we start from the smart connection level, data to information conversion, cyber level, cognition level, configuration level. So these are the different functions of Industry 4.0. I'm not going into detail of this because of the time limitation, because I want to touch something interesting for you people. And this is the convergence of IT and automation. Like this is the way IT has enhanced from direct digital controller, remote input output logic controller, field bus protocol architecture, and from mainframe ERP, Internet of Thing, Internet IO, PLCs, SCADA, MES, ERP. So this is like thing. Then this is what I wanted to talk about, digital thread for additive manufacturing. This is one really, so whatever you are doing, actually that is being done uh, parallelly, and that's what we call as digital thread. So this is like digital thread additive manufacturing begins. The broad one, these broad lines are basically digital thread. You can see the movement of my laser, and the dotted is digital twin actually. So you can see digital twin moving in parallel. And so what we do is that, so we start making with a model which can be just by designing or scanning and designing, and this helps in digital twin, which is basically runs parallel to digital thread manufacturing. So whatever you are doing in practice, a parallel or virtual model is also being created. So CAD model is generated. Then CAD model is analyzed in a traditional analysis way through FEA software. Then we go for multiphysics modeling and simulation. Then you go to the building and monitoring the things. So there's a build simulation, detail build plan, machine data. This is like part fabrication 3D process, in situ monitoring, and this is per part post processing and finishing. And finally, we go for testing and validation, so data verification and twinning. And this is where the digital twin is updated and being end. And this is through internet. This is being transferred to field sensing and testing. So the entire DTM digital thread, DTM stand for digital thread additive manufacturing, consists of four things: the scan, design, and analyze, the blue one; the red one stand for build and monitor; the yellow stand for test and validate; and the green stand for deliver and manage. I'll quickly go through all these four one by one. So it is basically a set of interconnected technologies that span and link the entire manufacturing process. And basically it gives you a capability to identify if a design fails or need modification somewhere. And it is also talking about scalability to turn the raw data gathered from the production of one part into applied process improvements. Uh, then we are talking about this is scan, design, and analyze. So this is like you can see. So from here DTM begins. This design and scan. DTM is digital twin is established. So a virtual model is established. CAD file is created. It is analyzed. It is uh, simulated. Then we go to scan, design, and analyze, where the CAD tools are basically taken into picture, and we generate for production the STL files based upon our inputs. So this is the view of the your maybe what you say the manufacturing part basically. So we start with the build simulation, detailed building plan, machine data. Then we have part fabrication, per part post processing and finishing. Then we go for the so this is like entire thing is fabricated. Then we go for testing and validation. So data is verification, and the same is the digital twin is updated in this case, and this is like testing and validation of the part which is being done. And finally we are like deliver and managing, and this is the point sorry, this is the point where your digital twin ends, but DTM continues till the end of the part, and the data is being transferred to the what you say is basically uh, the for the inspection and testing purpose also. So this is how the DTM and digital twin basically works like the for the entire starting from design, fabrication to everything. Okay, so these are like uh, one of the very uh, advanced technically, and digital twin, as the name says, it's a twin. That means it's a digital replica of any, it can be for any living or non-living things. But what we are talking about is basically we are talking about twinning of our entire manufacturing process. So the process which was carried out in a physical mode, we parallelly carried out in the digital mode, and that helps save a lot of time. And the best thing, as I told in the beginning also, some of the processes or parallelly we can do everything in Tokyo, in New York, and in Jabalpur. Uh, Physically we can carry it on only one place, but digitally we can carry it at different places. And so last thing on my slide is I'll take up some real life application which we have carried out at our laboratory. So this is for digital twin for the smart manufacturing, for additive manufacturing of our laboratory. So the process started with the generation of the CAD model, then the uploading of the printer, sintering, printing and sintering. This was the technology which we have discussed other day also. So this is like the paste extruder and the pellet extruder, the additive manufacturing setup which we have developed. And this is like the controller which we have developed for making it a smart device and sintering firmness. So this is a snapshot view of customized 3D printer. So material extrusion based 3D printer, and this is IoT enabled PC based controller. So entire process can be controlled from there. And this is a metal clay extruder. And ultimately, we can control it with the help of our mobile phone also. And these are the two models of fused metal filament fabrication which are developed and running. And these are like this can be controlled by internet, or these can be controlled by your mobile phones also. So I can run these machines, control the machines from my mobile phone, sitting at anywhere or at any place. Okay, so I have to rush through slightly faster the last few slides so that we can have some discussion. So these are last slide of my presentation before I go to references and other things. So IoT is not complete nowadays because it still faces many challenges. Like the first challenge is scalability. You cannot extend this process to a large. Then technological standardization, interoperability, discovery, software complexity, data volumes and interpretation, power supply, interaction in short-range communication, wireless communication, and fault tolerance. So these are some of the challenges, and mainly the mechanical engineers can look into the scalability, technological standardization, uh, fault tolerance. These are mainly primarily related to mechanical, but then if mechanical engineer can learn somewhat of electronics, somewhat of programming, which is a need of the hour also, probably we can address all these issues. So these are like a huge set of references which we have used for making this presentation. And that's all from my side. I think I finished within the time which I have assigned to me, 1 hour 15 minutes. We are open to any questions.
Sir, I can see a question on the chat box.
Yeah, please.
Sir, in smart manufacturing, what about material handling between the machines and between store and machine? And
That is
also,
also a part of smart manufacturing. As I told you, smart manufacturing is it is. Please understand what you are talking about is also automation, which was also Industry 3.0. But when this material handling and display is controlled by internet, so you have, for example, you have a data warehouse on the outskirts of the city, and your factory is on the other end of the city, and you can control the movement of the material as per the need in batch sizes, or even in the same plant from your storehouse to the machine without really involving human beings. That is also smart manufacturing.
and sir, what about the material storage and retrieval?
So same thing. It's the same thing. Everything is same actually. Storage and retrieval is also like conventionally in Industry 3.0 we were having automated storage and retrieval systems where just like your collet of a CNC machine, multiple tools can be holded. You can have a robot type of configuration which can store the material in storage houses with some RFID tag or some digital identifiers, and then when the material is required, the device goes in and sends the data and pulls it out. So those operations were done with a hard program. The programming and the control was done on the same shop floor. So from the computer center over there, and that computer center was used to send machines and controller. Now we are talking about the thing where I need not be present in the shop floor. I may be traveling anywhere, and I can control that same storage and retrieval system with the help of internet. So the connectivity issues become more uh, interesting actually in this case.
So second question is, kindly tell where is EDCM machine located?
Machine?
Kindly tell where is EDCM machine located?
EDCM is actually I was researching at IIT Kanpur. So one of my teachers, Professor VK Jain, has developed a machine over there, IIT Kanpur, and like there are some machines also in India. Probably I know about academic institutions. I'm not very much sure at this point of time the location of the machines industry, but IIT Kanpur has one machine. Probably IIT Delhi also has one machine. And if you want to get it done, um, there is a company called I'm forgetting the name starting with M actually, not MTab, but there's one more company, Pune-based company. They on your customized order, they make that machines also.
So the other question is, can we say that IoT and smart manufacturing might lead to unemployment?
And that's an interesting question. Actually, many people say like this, but technology never leads to unemployment. Actually, technology only leads to change in the role of employment. So from like shop floor jobs, now we need to work on more interesting, more technological intensive jobs, and like for example, the role will change, but then the you can see that the variety of components which we were looking at 10 years back has enhanced substantially now. So that when the variety of components, variety of products increases, the the production keeps on moving ahead and ahead.
Sir, another question, can you explain assistive technology tools and its application in the society?
So assistive technology tools are basically those tools which are assisting one primary technology. Like for example, I told you laser assisted turning or laser assisted grinding. So now if when you are trying to machine a hard to grind material, then with a conventional turning tool or conventional grinding tool, it becomes very difficult. So we apply laser energy on that particular material. Laser being able to impart the heat is making the material soft, and then this soft material can be machined easily. So because new materials are coming into picture and machining them is a big challenge. So these types of problems are addressed by these assistive technologies. And that's the benefit to society also, because you are able to make a component with new material which offers immense advantages as compared to conventional set of materials.
We now need to go with Industry 4.0 for mechanical engineers.
Please repeat your question.
With what level of skill we now need to go with Industry 4.0 for mechanical engineers?
The door is open for every skill actually, right from designing new machines to new processes to new communication channels, new devices, new sensors, new protocols. So everything is in R&D phase actually. Interestingly, it's not fully developed, but people have also parallelly started working on Industry 5.0 also, where most of the things are controlled by voice commands. Like, I think many of you have been using your Google Android Assist on your Google Android phones, or maybe those who are using iPhones, they use Siri. So like command by voice control command for Industry 5.0 is also, rather than simply your internet, it is also by voice command, which is happening. That's Industry 5.0. So, but then as I said, it is like the demarcation zone is ending very quickly and is moving very fast actually.
Sir, can we take that steps you explained for smart manufacturing in additive manufacturing are more or less the same for other manufacturing methods with smart manufacturing concepts?
No, I couldn't get your question. Will you please repeat your question?
Sir, can we take the steps you explained for smart manufacturing in additive manufacturing are more or less the same for other manufacturing methods with smart manufacturing concepts?
Yeah, we have taken this step for the additive manufacturing because I told you in the beginning of my lecture, beginning of my talk, that I primarily work in the domains of additive manufacturing, hybrid manufacturing, and smart manufacturing. So I have applied it for additive manufacturing, but then people can apply it for any domain and any process. The steps will be more or less same.
Sir, another question. So many questions for you, sir. I'm sorry, but sir, will you please explain the term intelligent machining in connection to Industry 4.0?
Vandana, your voice is cracking. I'm not able to hear anything what you spoke.
Sir, if Sudipto, sir, can you please?
Now you are audible. You can read it. Please read it.
Okay. Will you please explain the term intelligent machining in connection to Industry 4.0?
Now again cracked actually. So
Hello, sir.
please.
Hello, sir.
Yeah.
Sir, will you please explain the term intelligent machining in connection to Industry 4.0?
Okay. So intelligent machining is basically intelligent machining has various aspects. So intelligent machining is, if I look from the broader sense, it is basically machining which works on the optimized parameters, which leads to minimal wastage of material and minimal consumption of process energy. Okay, so and which can adapt to the process. So any industrial and any manufacturing process will become intelligent if you add some stages where even the machining can take care of decision making. I can take one small example to help you understand. Suppose you are manufacturing a block made up of heterogeneous material. Now, heterogeneous material will have different pockets of different materials having different hardness. So if you go for the conventional manufacturing technique, probably you have to take the tool which is capable of machining the material of the hardness or the toughness, and you have to pick up your process parameters, your cutting speed, depth of speed cutting also, based upon the toughest material. If you go for intelligent manufacturing, which primarily works on the real-time data analysis, so you get constantly feedback from this thing. So then as soon as there is a change in material, the process parameters will change. And if we have some other add-ons, like for example, if we had a system where energy can be given to the component, so probably before you move to machining of the hard material, that particular segment of the material can be heated, and the machining may take place at that particular domain. Okay, so that is the intelligent manufacturing. Like for example, I start forming a material with the two different tools. So what may happen is, based upon different formability, the tools which are initially in contact with the workpiece, they may lose contact. So what we do is that we should sense in real time that this contact is being lost, and accordingly, or maybe more force is being applied as than required, and immediately corrective actions are taken care by the tools so that the desired force is working within the range of tolerance limit. That's what we call intelligent manufacturing. So when you combine this intelligent manufacturing, when you are doing it simply by writing your codes and doing everything on the shop floor, that's a conventional intelligent manufacturing. But once you connected with maybe you can change this, like if you have developed the capability where you give me any geometry, any combination of different materials, any type of heterogeneous material, and I am capable of taking that decision, whether sitting on the shop floor, whether outside, that becomes smart intelligent manufacturing. Am I clear?
Yes, sir. Thank you so much, sir. Sir, it includes, that means it can include the machine learning also within the.
Yes, it can include.
Okay, sir.
So machine learning and AI are just tools which are meant to augment the capability of systems, actually, whether it's a manufacturing system or any other system.
Yes, sir. Thank you so much, sir.
Any other questions, please? Anybody has any other question?
Good morning, sir.
Good afternoon.
Good afternoon, sir. You are discussing about the electric discharge machining some slides back, sir. Actually,
what was I discussing?
Electric discharge machining, sir. EDM. Is there any? I mean, in terms of the research perspective, or like for submitting any proposals, like for DST something. So what are the latest topics which we can go for any these research proposals, sir?
So there are many domains actually. If you are interested in EDM only, so yes, EDM sir. Has still many challenges which you can look. One such challenge was I told you, like, about machining of the non-conductive materials, but yes, then process parameter optimization.
No, sir, my question here is in line with the industry 4.0, what challenge we can go with that? That's what my question, sir.
Okay, so again, I have told you what industry 4.0 is, and yes, you know about EDM. So yes, and I told you, like, scalability is one such issue which is still being worked out. So if you can maybe if you can convert a conventional EDM into a smart manufacturing setup by putting sensors, by putting communication protocols, and maybe if you can make it intelligent by taking a call on a different, like for example, if your system can automatically change the process parameters based upon different types of workpiece material you are machining, and maybe take a call on what is the right type of electrode material, that can be EDM in context of industry 4.0.
Okay, sir. Thank you, sir.
So any other question? I can take one last question, and then otherwise I'll close it out.
Any other question, please? I think that's all, sir. Thank you very much. It was really a very informative session for all of us. Anybody still want to ask some question? Sir is still open for a minute or two. If you still have a question, he can answer that. And if no, then we come to the end of the session. I once again thanks sir for joining and giving us so much knowledge about hybrid and smart manufacturing, sir. Thank you so much, sir.
Thank you very much. Thank you very much. So I'm leaving.
Yes, sir.
Thank you, Anna.
Participants are requested not to leave.
Madam, your voice is breaking.
It's raining heavily. Can you hear me? It's raining heavily at my place. Can you hear me, sir?
Madam, it's breaking.
Whatever, sir. But sir, there is a network issue at my place.
Madam, you put your message in the WhatsApp also.
Okay, sir. Okay. We can at 2:20. For feedbacks, lines are open in the portal. You can enter. There's a number you have joined, or should I take the attendance once again? Do I need to take the attendance once again? I think some of them have be advisable to take the attendance. Okay? Anyways, we'll join at 2:25. Thank you. And please remind me once again. Somebody